Okay, great. So the first step that we have to do is get onto the cluster. And as I mentioned in the brief introduction, we'll use SSH. And the way we do it here is we use SSH, your username. So this was part of your initial email with the credentials. We'll use the IP. So in my case, I saved this IP beforehand. So this is the current IP. This should be the same for all of you. So it's 52.30.38.106. If you press OK, you will be prompted for password. This password would be good to save somewhere. So I've done so. So I can just copy, paste, and then you are on the cluster. You will get some startup information on the cluster, so it uses Ubuntu and so on. So if you look here into the folder, you can already see there are several files. There's a README file, there are some job scripts, and it's also a Python script. And we'll talk about this all whenever they are, whenever we actually need them. So if you took a look at the README, so in my case, I will use Vim to navigate files. Feel free to use, I think Nano is also available and other stuff like Emacs or whatever you want to use as your text editor. And the README just has some general information. So the compute nodes we have today have 192 cores. These are AMD nodes. We have everything pre-installed for you. That means you have FHI-aims pre-installed. You have the Python environment pre-installed. So every package we need for today and all the different Python libraries are already installed for you. So you don't really have to do anything concerning the setup. We have put in some limits for the amounts of nodes you can use and job runtime and so on, just so it's fair for everyone and everyone can run through the tutorial. As we see throughout the tutorial, we try to keep the actual computation time as minimal as possible. If you want to do the actual analysis, and I will do the same, please first copy the files to your local machine, because I think we have not enabled visual external access to the cluster. So it's much easier to just copy the files with the save copy comment here, first to your local machine, and then analyze the plotting outputs and so on. But you will see this also throughout the tutorials. It will be the same thing that I'm doing. And so that's the README. There's some more information here. We'll go through it as we need it. So first, I just want to ask you, in case you are struggling to get on the cluster, I will give you a few minutes now to get on the cluster, maybe 2 minutes or so. Remember, the comment, as I said here in the beginning, is SSH username at the IP address. So this IP address will be the same for all of you. The username will, of course, change. You will be prompted for a password, which you then have to enter. It's slightly different if you're on a Windows machine, but those instructions have also been sent to you beforehand. So if you are struggling to get on the cluster, please let us know. So you can use the chat function, even the Q&A function, or the tutorial Slack as possible communication channels for us. And then please let us know before we start. Again, so we'll continue in 2 minutes. If everything is fine, feel free to just wait for these 2 minutes. Otherwise, please raise your hand or ask a question and so on. And then maybe it's good if James or Andre can post the links to the tutorials again here in the chat, just so that people also have it on Zoom. So we'll do so in a second in case you have not opened these windows yet. Yes. Thank you, James. Okay. Then I've not seen any complaints so far. So I would assume now that everyone is on the cluster. If that is not the case, please raise your hand, ask in chat, ask in Slack, in our tutorial Slack, or some other way. So we can try and help you. Otherwise, let's continue. So we'll start the tutorial today with the first part, which is here on the right. And it's on finding transition states or the minimum the minimum energy path with AIMS chain. So AIMS chain in general is a Python package which combines various flavors of different methods like the nudged elastic band, string methods, and so on for finding minimum energy path. And AIMS chain is really tightly integrated with FHI-aims. So a lot of you have probably heard already of different methods for finding minimum energy path throughout your research. So there are, of course, many different packages one can use, such as ASE or other external packages. But in this case, we really focus on AIMS chain. The main reason is here it's really meant to be used with FHI-aims. And it does not behave as much of a black box as some other calculators in our experience do. So we hope this is a nice introduction for you. As I mentioned, you actually don't need to look into too much detail on the preparations part, because of course for you, everything is already installed. But just as a reminder here, so of course you need FHI-aims. You need AIMS chain. So AIMS chain is also just a pip package. So it's a Python 3 pip package, which you can just install, as well as on optional CLIMS, which is our command line interface, which you don't actually need for this tutorial, but it's always good to have in case you want to do some additional post-processing or so. And we'll start here with a very brief introduction to AIMS chain, and this will already feature a very small example calculation we run. So the general problem here, as I mentioned, is always the same, right? So you start from two distinct configurations of your structure. So you have a starting and an endpoint, meaning as an example here, for the ammonia molecule, you start with the configuration here at the top, and then you say, I want to invert the molecule, right? So here you move down the atom, so you have a starting and end position, and then you want to find the minimum path between the starting and end position. And the way we do it here is really, you want to relax all the images, the intermediate images that you have between the starting and end points to find, as I mentioned, the minimum energy path with the lowest amount of forces. And we have several methods implemented in AIMS chain. So we have the nudged elastic band method, which most of you probably know by name. We have the string method and also the growing string method. They all behave similarly. So of course, the end goal is always the same. There are slight differences. If you're interested, we can also go into some more of the details. Of course, this is more a mathematical thing and the difference. In principle, we have seen that the string and growing string method behave slightly more stable and better than the nudged elastic band method. But this, it's not really a general, I would say, recommendation. So you can try out, of course, all the different methods that we have. So let's look at the ammonia molecule now. AIMS chain itself requires several input files, which I mentioned here. And as I said already, it's very specific to FHI-aims. So if you know FHI-aims, you've already seen something like the control.in file, which controls our computational settings, the geometry file format, which we usually call geometry.in. So in this case, we gave the names as the initial ini.in and the final fin.in positions, as well as the chain.in file, which controls the main setup parameters. So we'll start with a relatively simple case. So here on the left, I make a new working folder for this. So let's call it ammonia inversion, which I'll go in. Of course, this is now empty. I will then create the chain.in file, which is also pasted here for your convenience. So you can just create this file, copy in the contents from the left to the right. And then we can speak briefly about what these comments do. So we have some mandatory settings in the beginning of the file. And this is the run comment. So you specify run_aims and then the run comment. So in our case, we'll just use MPI run with 8 MPI tasks and the aims binary. And then mandatory, of course, is what is the initial geometry. So that's our ini.in and the final geometry, fin.in. And then afterwards, you can specify more options. So this is only a subset of possible options, but this is really meant to be, let's say, more or less the minimum amount of options you should set to run a minimum energy path optimization. So we'll use the string method here. You can also use the NEB, natural elastic band, or the growing string in this case. We'll use a total of 9 images between the initial and final points. So this controls, as I mentioned, how many initial points, how many intermediate points you actually want. And the force criterion, so this is really the threshold where we say the calculation is converged. So in this case, 0.01 eV per angstrom forces on all these intermediate images. Okay. Later on, if you like, you can, of course, play around with these settings and see what changes and so on. Notice here, we are not doing a climbing image search. So if you're familiar with these kinds of transition state finding methods, there's also the climbing image infrastructure, which is also implemented in AIMS chain, but this is something we'll not touch here in the tutorial. But just so you know, it is all there. And all of the settings for AIMS chain are also more explained actually in the FHI-aims manual. So if you take a look at the menu for FHI-aims, there's a full section also on AIMS chain and all the different options you can set. So we'll continue. That's chain.in. And then we have here 3 files we still need to create. And we'll do so now. So we have an ini.in, which is the initial file, the initial geometry. Notice here that this is really specific to FHI-aims. We are using this constraint realization keyword, meaning the first atom, the nitrogen here, is fixed in its position. In principle, this is not needed, but it's much faster to optimize this minimum energy path if you constrain the first atom, the nitrogen. So, and as we mentioned, because it's AIMS chain is really written for AIMS, FHI-aims, it knows all these keywords. So throughout the calculation, this atom will actually be constrained also. Then we do the same for fin.in. Copy in fin.in. So now we have the initial and final geometry, and then we still need to give the different files that we need to run the actual FHI-aims calculations for all of the images, right? So in our case, we'll use the PBE functional. We use a van der Waals correction. In this case, this is just the TS method, the relativistic correction, a charge mix parameter. So this is really only to speed up the SCF convergence in this case for the molecule. And we need the forces. So this last keyword is, of course, very important because for any kind of minimum energy path optimization, we need the forces in each calculation. And FHI-aims by default does their computer forces. So please remember to always put in this specific keyword, compute forces. So we do the same again to create a control file. Copy in. As you can see here, we also already have the species attached. So if you've seen the video on the basics of FHI-aims or used FHI-aims before, here we are using light species defaults for all atoms. So light is already, as the name said, quite computationally efficient, but it actually does not have the worst accuracy. So as you will see later on, the results are already quite good already with light basis settings. And then, and then we'll save this file. And now, if you look into your folder, you should have 4 input files: chain.in, control.in, fin.in, and ini.in. So in case you're still on this part, we'll wait a minute or so for you to all set up these files. Of course, if you're struggling, if you have questions, please ask. So raise your hand, ask them in chat or wherever. Just so we know. Otherwise, I'm always assuming that you're all already at that stage. Okay. I don't see any hands or questions in the chat or Q&A. So to me, it sounds like everyone is fine. So now we need to actually run the calculation. So we have all the input files that are needed, and we have to run the calculations. And to do so, we can use this submit script here, which we have written. So this is specific to the cluster we are using. So if you have a different cluster, please remember this whenever you do this on your own time. So in our specific cluster, we'll just create a script. So we call it submit aims chain.sh, copy in this content. So what we'll do is we'll use not a full node, but always just a node with 8 tasks for 10 minutes. And then we need the run chain command. So if you install aims chain with pip in your Python environment, then you can just use the run chain command to start the calculation. So then, as you can see here, we can submit the calculation. So for that, you need SBatch. As I mentioned, we use Slurm as the submission script, submission system. And SBatch is the command to get on the queue with this job. So we copy in the command, SBatch. And then you can type SQ to see what happens. Now we see several users have already submitted a job, right? So Leon, this is me. And you all have your user 06, 28, and 10, and so on. And you can use this command to also inspect what's going on, right? So here, for example, we are running 15 seconds. If you look into your folder, you will already see you have new input and output files. So you have error and output files. These are just from Slurm itself, from the batch system, just giving you some information in case there are errors and so on. And aims chain will create several files, which are also mentioned here on the right. So we have a log file, which is called forces.log, which contains the total amount of forces for each of the different iterations. We have the different iterations and the paths, right? So the iterations, or let me start by just looking at the forces. As you can see here, so we started with an iteration 0, 0, 0, and the residual forces are quite large. And the reason here is pretty simple. In the beginning of the calculation, it assumes a linear interpolation between starting point and end point. Typically, linear interpolation is not really optimal for most cases, meaning in this case, that's also the case. Here, the energies, the forces are quite large, but they are, of course, here subsequently reduced. So if you inspect this file, you will see after some iterations, so in this case, 6 iterations, we have a residual force which is below our threshold. So remember, we defined the threshold to be 0.01 EV per angstrom. So after 6 iterations, this seems to be converged. Great. Then we can take a look what kind of files we now have. So we have an iterations folder. And if you take a look at the iterations folder, it's again, you have all the different iterations 0 to 6 in different folders. All these files here are binary files which contain restart information. So by default, you can just resubmit an aims chain calculation. It will restart from the last last point in the iteration here. So if you take a look at the iteration folder, I will just use as an example here, you will see that all of these nodes. So remember, we have a starting point, so that's 0.0, and an endpoint 1.0, and in between we wanted 8 points, and that's exactly what aims chain does. So it has 8 points in between, does the calculation, and so on. And the first and last one you only need in the beginning. So you will notice that any other iteration than iteration 0 does not contain any more 0.0 and 1.0, because these are meant to be fixed. So we only need to calculate these energies and forces once. Okay, so if you actually look at, as an example, one of these folders, you will see this really contains the FHI-aims output files. So this is really the raw data that is used to compute energies and forces here. Then if we go back, as I mentioned, we also have an optimized and path folder here. In the path folder, you will find the structure files for all the different iterations. So as an example, we can look at iteration 0. It will give you all the images. So these are all the optimized images of the full path with energies. And also, again, an overview in a .list file, so that's just a text file, and an XYZ file for visualization, which we'll look at in a second. And then if your always a good check is if your calculation converts, you will get an optimized folder, and this optimized folder has essentially the last path in it, including end starting points. Okay. Any questions up to here before we go to the analysis of this part? Let me check if there's some people. Yeah, there's someone still running something. So this seems to be pretty long. So maybe you have to check your geometry again. So if you go back up here, user 15, it might be that you have the wrong starting and end point. So please make sure. So as you can see, what is the difference between initial and final? Well, we just add a minus to the z coordinate because the only thing we're doing is inversion. All right, so please always check that this is the case for you. So it might be that you used the wrong geometry in one of these. And just in case you're not sure how to cancel a job, you can run, for example, so user 15 in this case could run scancel and then the job ID, which is the first entry here, to cancel the job. So if you see that this does not work, you can run this comment here. So in your case, so if you're running the first example, this is way too much time. So I'm sure this is the error. Yeah, the residual force. So there's a question from David in the chat. Is exactly the maximum force of the set of images. Correct. That's essentially, as you know, whether it's in the string or NEP calculations, what you're optimizing is always the perpendicular component of the forces compared to the path, right? So if we minimize the perpendicular component, that means you're really getting pushed towards the minimum energy path, and that is what we are tracking here with this residual force. And if this is below for each of the images between a threshold, that tells you it's you are as converged as you want to be. Okay. Okay, now I don't see anything. Good, but we can already now, in principle, continue at least with the copying step, right? And in this case here, we'll start before copying all the results, we'll just plot some and then look at them on a local machine. So we prepared, that's a very simple plotting script. So in your folder here, you can create a plotting script. In this specific case, we actually go into the optimized folder and create it. So go into optimize, then here create a plotting script, plot.py, copy in what we have on the right. Sorry. Copy in, save. So it's really opening. So it's opening the energy.list file, which I'll show you in a second. And this is just really giving you the energy of all the different images, right? So you have the initial image, the final image, all the images in between with relative energies. Then you can just do python.plot, python-plot.py. This should run. As I mentioned, all the environment is already set up for you. So as you can see, we have this aims environment, and this already contains all the different Python libraries you need for this tutorial. This should give you this plot.png file. So before we open this file, as I mentioned, we can't open this file here. So we'll go back. I run the pwd to get the current working directory. Yeah, and the full path. So that's my working path. It might be slightly different for yours. And here, this is my local machine now, and I just created an empty folder. And the only reason I'm doing it here is so I can copy over this path. So what we do is, again, username at the IP address, same as you used to log in. You then do a double point and the path to the folder that you want to copy. And then we do so here. You will be prompted again for password. Which you can enter. And then it will copy in all these files. So this is not the fastest here. I just show it to you now. As we see later on, when we do the other tests, we will actually, instead of copying the folder at once, the problem is now in the folder, there are several individual files, and you have to copy all of them at one after the other. That typically means you have to initiate a transfer between the data every time a new file is touched. So an easier option, as we'll see in a second, is to first create a zipped archive of the full folder and then copy that one, and the time will be significantly smaller. So as you can see here, it will copy now all the different files. As I mentioned, AIMS chain actually stores all the input and output files. So if you want to examine also the actual AIMS calculation later on, you can do so because we have all the output files here. Okay, so this is really all the raw data. If you are used to some other packages like ASE, you typically do not store the raw calculator data, just the post-processed one. So that's why it looks like. Yeah, exactly. So David, as you mentioned, there's an option also in rsync to do so, to compress the data before then sending it, which you can also try out. I just wanted to show you here the first blanket copying step. And as you see here, this takes a while. This is a general problem. So if you want to, if you work on a cluster and you have to copy your stuff over and back, it always makes sense to compress it. We can try the comment after from David also in another exercise. So we go to the ammonia inversion. And now, as I mentioned, in the optimized, we should now have a plot.py, plot.png, sorry, and this we can just open. And then you get an image, which luckily, of course, matches the solution that we have here on the right as well, right? And what you can see is the barrier for this inversion is roughly 0.25 eV. Yeah. So, I mean, in the end, if you actually check the results, it's like 0.236 from the output, which is already quite good compared to a reference value. So that's also a theoretical value, but yeah, it's usually around the 0.25. Good. In case you're interested in, so I use the same path here to visualize the inversion. You can use several packages to do so. Just one is JMOL. So in case you're aware, JMOL you can just download for free. If it does in the same folder here, there's an XYZ file, which you can just load. And then you can do an animation right here, which you can see here. Let me just, yeah. So you start from some point and then you invert the molecule. And that's how it looks like. Right, so AIMS chain by default writes you also this XYZ file. So you can take a look at the resulting path. Okay, so that's the simple ammonia inversion. Is there a question on this part before we continue? So just as a spoiler, so the next part will be on diffusion barriers in solid electrolytes, which is actually the example that Alexander Chachenko showed in his talk yesterday. So is there any question before we continue on this? Sanuya, yes. I will allow you to talk. So you should be able to talk now if you want. Hello?
Hello?
Hi.
Yeah,
Yes.
can you hear me?
Yes, we hear you now.
Yeah, actually, sorry, actually, I did not understand how to generate the intermediate images.
These are generated automatically.
Okay.
So I can show you again what that means. So as initial and final input, you only need to give the initial and final positions, right?
Okay.
So this is done here. And then if you specify only a number of images in AIMS chain, so in this case 9, so we want 9 in between starting initial point, by default it will use linear interpolation. So we'll just draw a line between initial and final, and then equidistantly create 9 of the intermediate images. Right?
I have that file also. In the file name chain.in. I have initial geometry file and the final geometry file also.
Mm-hmm.
Then I have to run the job, right?
Yes. So that's with the script here.
Okay. I copy the submit subscript file from the home directory.
Yeah, that's a wrong one. So this one here. Oops, sorry, it's a wrong. So if you look at the script, so the FHI-aims job here is slightly different. Why? Because this one, oops, will be used in the other part of the tutorial because we use the AIMS file directly, binary here, right? Here we need to use the AIMS chain infrastructure. So the comment is different. So this one will not work for this part of the tutorial.
Okay, that is the mistake I did. Yeah, thank you. Okay, I will run it and let you know.
Yeah, exactly. Just let us know if it doesn't work anymore. Okay, so there are 2 questions in the chat. So one is very easy. In which program do you do the animation? So this is just JMOL. So if you just Google JMOL, you can directly take a look here. The animation that I'm doing here is not JMOL. This is actually Ovito. So if you know Ovito, this is also a quite nice, I think, visualization package. It also has a free version. So in the pro version, in this case, I just used the free version to create this animation. Then there's another question from David. How can you generate the path if you have a rotation so you cannot do a linear interpolation? So there is a way which is included in AIMS chain, which removes essentially the rotation already. So one thing is, that's a user problem. So you have to include somehow already initial and final positions that make sense where you remove the rotation if possible. Otherwise, within FHI-aims, you can also remove rotations for molecular and atomic-like calculations. So if you have a non-periodic calculation, you can actually remove the rotations also from the finer forces. So yeah, it's a user-specific thing in this case. So you can, of course, rotate. I'm not completely sure how that will work in this specific case, what actually happens then. There is also this growing string method. So the growing string method is slightly different in that it does not do the linear interpolation, right? So in the general case, I think if you want to do rotations or something, it's probably best to use something like the growing string, because here the path in the beginning is not directly just given as a linear interpolation or so. Right, so you can use the growing string method in this case. There are other methods which are not implemented in the AIMS chain at this point, which I think try to handle this initial path generation. But what AIMS chain can do, and this is what we see in the next section, if you have an initial path already from intuition, other packages, and so on, you can use this as the starting point, and then AIMS chain can just directly optimize your path. So, but this is exactly what I'll show you in a second. So you don't have to start from linear interpolation, but you can. So yeah, that's just the point. So you could try growing string in that case directly. That does not mean that growing string does not need a linear interpolated path. I hope that answers the question somehow. You would have to try it out. I'm not completely sure. So that's not my in my working field, so I don't do much of these calculations, but let us know if that works or not. You can try it out. Okay. So I don't see other questions right now. So I would continue with the second part, which is lithium diffusion in solid electrolytes. So there's a small introduction here. So I will just for now, close the animation here, just so it's not disturbing anymore. Okay, so we did the ammonia inversion. So I will go back a folder because here we'll use a different one in a second. So AIMS chain can, of course, does not have to be just a simple inversion stuff. It can also be, of course, used for solids. So in our case, we're trying to look at the solid electrolytes. And this is really exactly the use case that Alexander Jurchenko discussed yesterday. So we are looking at this R-gyroids, right, which is this lithium-6 MS5X structure, which, as you know, and also saw in yesterday's talks, if you were there, which is one of the promising solid electrolyte candidates right now, right? So these are sulfur-based, and this is somehow what the structure looks like, right? So if you remember, you have this phosphor sulfide tetraheders, which are more or less fixed. So these are distributed here throughout the crystal. And then you have also some sulfur ions, but you also have these lithium ions, right? So the structure itself is quite complex, and that's also visualized here by this partial occupation. So if you see the white and green dots, these are meant to be partially occupied positions. And in reality, these are two different Wyckoff positions. So the two outermost are Wyckoff, I think, 48H, and the inner one is 24G. So that means each lithium ion can be in one of these three positions at one time, but not in all of them at the same time, right? So now you can imagine, of course, you can create then several of these structures depending on where the lithium is positioned. And what was done in the publication that's already accepted in Nature Communications from Banerjee and Jurchenko is that they looked at several of these configurations and then took essentially the lowest energy one to further analyze. And we'll do the same in this tutorial. So that's the general structure of this system. And that's, as you can see already here, quite complex. But the important thing is that these lithium ions here can diffuse throughout this crystal. So these are really mobile ions. And that's, of course, needed in the solid electrolyte case because we need lithium ion diffusion to get high conductivity values. Okay. One thing which we'll show for one example of a diffusion path in the system is how, one, we can calculate it with AIMS chain, and then also compare different methods to see what gives the best results and maybe what is the reason some give worse results than the others. Okay, so that's just the relatively short introduction. If you have questions, of course, throughout, feel free to ask. So we go to the actual tutorial part now. Here, so the computation time is quite short. So we estimate, and on our resources, it's a few minutes, 2 or 3 minutes, I think. So less than 5 usually to get all the calculations done here. So this is the supercell that we'll look at. So this is this lithium-6 PS5I structure. So I just call it LIPSI for short. So in case you hear LIPSI, this is the same structure, right? So you have a cubic space group. And this is the 2x2x1 primitive cell of the system, right? We're doing here the 2x2x1 because this is the same one that was done by Banerjee and Jurchenko in their paper. And we are doing only one specific one. As you saw in the previous picture, in principle, you have partial occupation, so many possible lithium sites. This is essentially the lowest energy one that they found and also looked at in their diffusion studies in that paper. So this is the structure we look at from now on. Okay. Yeah. If you have any questions here, feel free to ask. What we'll look at is an intercage lithium hopping with roughly 3.3 angstrom. So it's actually here on the border of the cell, and you'll see it also in a second. I quickly scroll down as a here. This is the path that we'll look at. And this is the simple linear interpolation. I'll go up in a second to create the files, but just as so you get a small sneak peek, this is what the linear path would look like. And you can probably already guess that the linear path is most likely not optimal, because you can see here, it's quite close to these neighboring tetraheders already if you would just do linear interpolation. So here it's pretty clear you have to somehow optimize the path. So, and the reason we are doing this specific intercage lithium hopping is just that this was done, the same path was analyzed in the reference publication. Okay, so that's the main point. So we go back up and start, right? As I mentioned here in the warning, of course, for this tutorial, we're all doing it with slightly less converged settings to get actual results, but all the qualitative trends are already there. So we'll start by creating a new folder. So this is done on the compute resources, which I just call libc diffusion. And as before, we need to create all the different files, right? So we need a geometry file, an ini.in. So this should now be familiar to you, which I'll copy in. And a fin.in, just in the next tab, right? Which I'll also copy in. Now, in principle, what is important for these kinds of calculation is that ini and fin.in are fully optimized with the level of theory that you want to calculate the energy path with, right? So I have relaxed the atomic positions. I did not relax the full lattice here. So as you see later on, this will not be the perfect minimum energy path with the correct barrier that you would expect, but it's good enough for us. So these are the internal positions are optimized, but not the full lattice here. So I think these lattice vectors are still the HSEO6 plus MBD values from the reference publication. Just as a disclaimer. So next, we need to create a control file. And the control file itself is similar to before. So we're now doing pbsol, which is also one of the functions that were used in the paper. We're just using a 1x1x1 k-grid. As I mentioned, we're not really interested in super converged settings. We need the forces, and we're using a slightly increased charge mix parameter to speed up convergence. Okay. So, and in general, in case you're unaware, charge mix parameter controls the mixing in the pooler mixer in the FHI-aims code. So we save. You should now have 3 files. So what is still missing? Oh, and by the way, the species defaults here are also the light settings. So the same as before, we're using light settings for all the elements in the crystal. Again, here it's mentioned also that you compute forces. So always check this, please, that you actually compute the forces. Then we need the chain.in. And the chain.in in principle looks very similar to before. So we are using still an MPI run comment. So this time we're using a full node. So that's 192 cores on our AWS cloud. The other parts here are the same. So we have an ini and fin.in. And there's some slight differences. So we're still using string. We're using less images just to reduce the amount of computational time we need. The force threshold is also larger. So we are not converging as tightly. The problem is usually the more complex the structure is, the harder it is to actually converge to very, very low force thresholds. And the other point is that at some point, a lot of it is also noise. So sometimes your barrier is not even, if you go to super low values, that does not mean it will actually reach those force thresholds. And your barrier might already be more or less converged before. So, but just keep this in mind. These are meant to be good qualitative results. These are not fully converged ones. So in the paper, they also used tighter settings, just so you know. So the optimizer here is the BFGS algorithm. This is not necessary for you to specify, but we just do it here. And this, I think, is also related to one of the questions we already got, which is here this external starting geometry. So in AIMS chain, you don't have to start from linear interpolation. You can start from whatever starting point you give it. So the way we do it here, we save this. we now need to create this external part, right? This is somehow explained here slightly in the text. So we still need to create an external geometry.list file, which is an input file that lets AIMS chain know, okay, these are the external geometries you want. And in a principle, it should correspond, of course, to the n images value. That's not necessary. So for example, if you start the calculation and you pre-converge a path with 4 images, and then you want to have a much more converged one with 8, 9, whatever, how many images, you can then also specify a resample keyword. So there's a keyword for AIMS chain, which you put in chain.in that can take this 4 image path and just resample it with 8 images. So you just interpolate in that path and you actually do 8 instead, or 9, whatever, instead of the 4 images. So that's just a slight comment here. So the simple linear interpolation would look like this, but this is not the starting point we want to do. And the main reason, as I mentioned, is, as you can see here already from chemical intuition, this would probably be a very high barrier to overcome and will not be the converged one. And I'll also show you later on. So we did the actual calculations from a linear path first, but these are too long to do in the tutorial. So we'll start from a pre-converged one. And to do so, we'll create first this interpolation folder. So it's all in the same folder where we are currently in. We create interpolation. And in that folder, we create 4 files. So 4 files for the 4 images we want to simulate, which we'll just call here image 002.in, 003, 004, and 005. Okay, so I'll go into this interpolation folder and then create all these images. So 001. Then I do the same, typo for 002. Oops, I messed up slightly. 1 second. Of course, the first image is not 1, but in this case 2, the way I wrote it. So change this. So you start from 2 and then you have 3. Then we do the same for 4. Then we do the same for 5. So your folder should now have these 4 files in this interpolation folder. Okay. So I'll wait. So feel free to take your time and do this. So I'll wait a minute or so. Again, if that does not work, let us know. Okay, so then you go back again in this folder. And then we still need this external geometry file. And that's needed for AIMS chain. As I mentioned, you can copy in just this content. So now AIMS chain knows, okay, it wants to, it should use these 4 interpolation images. So now you have 5 input files as well as this interpolation folder with 4 input files. So it should look like this before you submit. So similar to before, we use a submit script, which we have prepared for you. Submit AIMS chain. Similar to before, we just now use the full node, so 192 tasks. Then you submit. Okay, so we submitted with SPatch again, and then we wait. So my calculations are running. So you again see these new path created, iteration, path, and the forces. So if we take a look at the forces, it's calculating. So currently it's still stuck on the first iteration, but this should hopefully be done relatively soon. I think it takes 2 minutes or so to do. So here we're just waiting. And now you could probably already tell why we gave you a p-converge path. So this is, of course, a bigger system. So I think it's like 52 atoms or something in the unit cell. So this is already a bit more expensive to run. Let me check the queue. Okay, so we have a lot of people running calculations. So in case you see the CF, that just means you are currently on a node, but that node still has to fire up. So this usually takes 2 minutes or something, and then the calculations will run normally. So because now we have a lot of calculations in queue, which is good. But yeah, just so you know, CF just means configuring. So it's currently in startup mode, but this will be finishing soon. So take a look again at our forces. So you can see here, the initial iteration is already quite good. So we have 0.1 EV per angstrom roughly of residual forces remaining. And that's just because we already gave you a pre-converged path. And it should only take one more iteration to converge below 0.1, which is also what we see here in the output. So this should not take too long and should be done relatively soon. So please bear with us a few moments. So the full node count can fire up. Perfect. So as you can see now, we enter iteration 1, and then we're below our threshold. So now it's converged. If you check our output, you can see now also the optimized folder. So this worked for us. So I know several of you are still in queue. So yeah, just know this will finish whenever this configuring statement is up. And as I mentioned, it takes a few minutes to run. Okay. In the meantime, you can, of course, already prepare the plotting script and so on while you wait. So you can take this plot energy path, which you can create in the current directory. So you don't have to go to the optimized folder now. So you can just create that path. So we just wrote this quickly to do some analysis. So it's not the most sophisticated one, but it takes the energy.list from a folder and the path.list to plot the final curve of energies versus reaction coordinates, right? And this is how you typically use it. So you can just do Python plot energy or whatever the file the name is for the script, and the different paths and the calculations. So in this case, we do Python plot energy. I'll just show it to you once, as again, wait for your calculation to then run. So here we just do the optimized folder. if you are converged. And this would give you a very short summary, like the minimum energy and the minimum barrier, and save that to a file. Right? So it should look like something like this, but I wait a few seconds for all the people here to finish. So it's at least these calculations. It will take, as I said, like 3 to 4 minutes to run the final iteration. So, but as I mentioned, the plotting script you can already prepare with the content from here and play around. So as an example, you can also do, if you don't already have the full converged one, you can just take one of the paths. So if you just do path iteration 0, for example, to get the first iteration, you can also do so. So you can see here, you get an energy of maximum barrier of 0.37. And here, I think, yeah, it's also already very close to the converged value, right? Which is as expected, because we start from a very well pre-converged one. Check the queue again. Yeah, so these should all finish up pretty soon. But of course, if you have questions now, feel free to ask now. So it would be a good time to ask. Yes, David, that's what I mentioned in the beginning. So in principle, you would have to perfectly converge the starting and endpoints, right? But as you can see here, you don't actually start from a perfect local minimum. And so that's what I mentioned in the beginning. So the initial and final files were not fully converged, meaning I did not converge the full lattice and atomic positions. I only converged the atomic positions, but not for the correct lattice. So that's the reason here. Yeah, no worries. No worries, David. So take this with a grain of salt. It's not the perfect barrier, but it's close enough for our purposes. And then how to find the minima points? Well, you just you basically you can do this. So in this case, this was done manually. So you start, this is just a normal crystal position that you have. Then you move the atom to there, and then you just relax both structures, right? So you relax in a separate calculation the first structure, and in another calculation the other structure. And that's how you find the minima. So this is a choice, of course. The user has to say what kind of minimas you want to sample. So I hope that's good enough of an answer. Okay, so it sounds like here, mostly finishing up. Okay, so let's go back. I will plot again the optimized folder. And this is what I'll copy over. So I'll then copy over, if you remember here, this was the Ammonian version. So I copy it to a new folder, right? And if you like, so for example, here, I could just try the comment that David also said. I could do minis A, B, Z, do a username at the IP, copy the folder, and then copy it in here. This prompts me for password again. Yeah, and it gets the full files, but it's all compressed. So yes, it's much faster than the previous case, as you can see. And now I have the diffusion folder, which I can visit with all the files. And you should have, if you run your plotting script, this energy path file, which you can open if you compare it, and then of course to the reference. This is exactly what I mentioned before. Okay, so this is more or less what it should look like. As I mentioned, the initial and starting points are not perfectly relaxed, and not perfectly optimized. So ideally, you would always start from 0, both initial and final, because it's like the local minima of the structure. It's not the case here. So you get a barrier of around 0.4 eV, which is already quite good compared to the reference. So they also get something around 0.4. Experimental measurements of the migration barrier, so that's an average over all diffusion paths essentially within the system, are around 0.39. So this is at least comparable. But keep in mind here, this is all zero temperature. So the calculation we have done are at zero temperature. If you include temperature, you would normally expect higher barriers from the DFT calculations, and they would be reduced at higher temperatures. So keep this in mind also. This part here is just a plotting script I showed for you. As I mentioned, we actually started from a linear interpolation on the results we gave you. So instead of the pre-optimized path, if you start from a linear interpolation, as you can see here, this is a huge barrier. So you have something like 1.5 eV of a barrier, right? This is significantly higher than you would expect, meaning also here the linear interpolation really doesn't make sense for this kind of path. And this is also what I can visualize here. So you can see here still in light gray the linear path, right? That was there first. And if you optimize, exactly as I mentioned, if you're too close to this tetrahedra here, this messes with your barrier. Instead, you go around it, right? Which is why you get this curve in the minimal energy path here. And then you get more or less the barrier that we also expect. So I hope that is okay for all. So we don't want to spend too much time on the actual details here, but of course you can inspect also the input and output files and visualize for yourself if you want. So again, this was done here with Ovito. You can also do the same with JMOL or any other, or not any other, but a lot of other types of visualization software. And then one thing I just want to mention, this was mentioned yesterday in the talk by Alex Churchenko, and it's also in the reference publication. So this is the exact same path that they looked at, that we just looked at, just compared with different methods. So GGA functional, as well as hybrids plus different dispersion corrections. And you can nicely see one, that with PBE Sol, the yellow line, they get more or less the same barrier that we have, so 0.4 eV. So that's already quite good, right? If you do the most sophisticated functional, meaning HCO6 plus MBD, you get a slightly higher barrier, and this actually agrees better with the experiment because we would expect from DFT a higher barrier than the room temperature one from experiment. But TS, for example, here, so the Churchenko-Scheffler correction, is actually quite bad, especially because it overstabilizes the transition state very drastically. As you can see, compared to local minima, this is a drastic overestimation of stabilization of like 0.2 eV. So that's just what we want to mention as a side note. So we use PBE Sol, but really, if you want the most accurate barriers, you have to go to more sophisticated methods for these kinds of systems. So on the solid electrolytes, we would recommend something like hybrid functionals plus modern dispersion corrections like MBD. Okay. And that's essentially this short tutorial. If you're interested in this dispersion stuff, we also have a separate tutorial, which we'll not talk about today, but this you can just also take a look at in your own time. So do we have questions on this part? Let me check the cluster quickly. Yeah, I don't see anything running, so that should be good. Is there any question here on this part? Otherwise, we move forward to the vibrational spectroscopy, which is not too long of a tutorial, but we still want to show you how to actually do those types of calculations. So any question on this part? Okay. At least I don't see any. So the next part would be the electric field response. So that's vibrational spectroscopy, essentially, corresponding to the talk by Mariana Rossi yesterday. So before I'll go back in here and do a separate folder on our cloud machine. So we're not talking about much of the details here, right? So I think a lot of you have already heard how or know how to do infrared and non-resident Raman in different codes or just throughout your career. So instead, we'll just focus on a simple example, which most of you probably also know quite well, which is just the benzene molecule, right? So we'll show you directly how to just do it within FHI-aims and what you need to do. The workflow here is quite simple in that sense. We just do in geometry optimization first, because of course now you have to have accurate forces if you want to do this vibrational spectroscopy. So we'll do the geometry optimization. You need then the Hessian matrix, so second order derivatives of the energy. Then we do, in this case, we do with finite differences. So that's also what Mariana Rossi mentioned yesterday. We typically recommend finite differences over the analytical part for the phonon-related properties in FHI-aims. So we here also only focus on the finite differences one, right? And then we can do diagonalization. So that's done in a post-processing script, IR intensity, as well as Raman intensity, right? So we need dipole moments for the IR intensity, as well as the polarizability tensors with DFT for the Raman. So we'll start here by just creating a working folder. So that's just called 1_benzene. We'll create a relaxation folder because we want to relax our initial structure. The initial structure here is a just geometry file. So I skip visualizing this, so I'm sure you all know how a benzene molecule looks like. But if you like, you can also just look at this in your local machine. So now we need really the ground state structure for this for our specific computational setup. So we use here a control.in file. With PBE functional, no spin. These are just the convergence criteria for the density. So we are pretty tightly converging the density because the density in turn gives you also converged forces. And then the relaxed geometric tag here is just relaxing the internal positions of the structure. So before we start, we still need to append the species files, so essentially the computational settings for all the elements. And to do so, we can use CLIMS. So CLIMS is also pre-installed on this cluster. So we use here the species light dense. The main reason why we're not using light, so before you've seen light dense is the same basis amount of basis functions as light, but it uses dense integration grids, which in turn give you more accurate forces. Yeah, there's a quick question in the chat. If you want to visualize geometry.in, exactly, you can use JMOL, you can use Vesta, you can also use GIMS. So if you want to use our GUI, you can just go to gims.ms1p.org. And there's also a structure builder. And here you can also import the geometry directly. So that's also a possibility. Okay. So now, if you check your control file and you ran this CLIMS prepare run, you should see now we have the light dense defaults appended here. Okay, so this is all good. Now we need to run the job. In our case, we'll use this script is already on the cluster, so you can just copy it. This is FHI-aims job script. We submit it. You should be on the queue. Some people are already submitting. It's very simple script. It just takes a full node and runs the aims binary in this folder. And you should already see there's a lot of output. It's already done. So if you take a look at here, in case you're wondering, how do we check if aims.out is finished? If you scroll down and you see I have a nice day, that typically means everything worked out fine. The calculation is finished. So now you have a geometry.in.next step. That's the relaxed geometry. You have a Hessian, which contains the estimate of the Hessian matrix, as well as the aims.out file, the standard output. So now the next step is we go back. We make a new folder, which is called displacements. Because now we did the relaxation. So now we have a good starting structure. And then we want to analyze the vibrational properties. So here we copy from the relaxation folder we just created before with the optimized geometry. So that's geometry.in.nextstep. This is our new starting geometry, but we'll use the same control file. So in displacements, you will have control.in as well as geometry.in. Okay. And then what's also mentioned here, so we need to add and remove some parts. Okay. So what we need to do is take a look at the control file. All these parts after SE accuracy row, which is on the right side, you have to put this here below the SE accuracy row output, setting. So, and importantly, you don't have to relax anymore. So please remove the relax geometry comment. So what are we doing? Well, we need the dipole, right? For the IR intensities, we need the forces. We want to clean the forces, meaning we remove the rotations because we have a molecule in this case. We have the polarizability because we need the polarizability from DFBT for the Raman intensities. And then we just put in some settings to converge the DFBT part faster and accurately. So this is the accuracy for the self-consistent first order density matrix as well as the mixing parameter. Okay. So, but as I mentioned, you can just copy the lines here from the right. So that's all we need. And this was all part of a recent restructuring of the DFBT part of the code. So now we just copy in the get vibration script, which is already in your home folder also on the cluster. And this is really meant to be a helper script. So it takes care of setting up the vibrational, also to calculate the vibrational modes and so on, right? So it does finite differences. It takes care of setting up the structures. You can then run the structures and then again post-process to get vibrational frequencies, vibrational modes, and in turn IR and Raman intensities. Okay. As we mentioned here, this is really meant to be a basic script for now. If you're interested in more sophisticated infrastructure, meaning non-analytical corrections for periodic structures, which are not as simple as what we're doing here, but we can't do also vibration cross sections, all this kind of stuff. So if it's something that you need, this is also something we can work on, but this will depend on whether a lot of people request it or not. Okay. So in general, the structure is as such. So you can just take a helper script here. You can generate finite differences and then calculate the modes as well as the intensities. So in our case, again, shown here in the run modes, you can just copy this comment. So it will create a Benz directory. And then here, 0 means it will generate the finite displacements. So we have found 12 atoms. We will use all of the atoms in the calculation. And now you will see a lot of different folders, right? And the reason here is pretty clear. So we have 12 atoms for finite differences, meaning per atom, we're doing finite differences. We have 3 coordinates per atom, and we do 2 displacements, so in positive and negative direction. So in total, you have 12 times 2 times 3. So that's 72 folders in general. So keep in mind here, this is not using symmetry for the finite differences, right? So if you're used to something like PhonoPy, you of course can use symmetry to reduce the amount of finite differences you need. I'm just mentioning here that this was not, in the current iteration of the script, this is not included. Okay. So we have all these folders now created. Now we just need to submit. The way we do it, so this is the script that we are using, but you can also just copy it, which is already on the cluster, which is called FHI-aims job loop. which is this script here. And then we just submit. So there's some stuff running still. So if you submit a script, you should see it's running. In case you are wondering how many calculations are finished, so you can actually, as I mentioned before, there's this have a nice day line at the end of the file, which you can just search for in all of the output files. And in this case, we just count the entries. So for now, nothing is converged yet. Right now we see a lot of different nodes. So for example, now we see that 24 of these calculations have been already finished. Remember, we need 72. So the way we do it in the script is we're actually submitting many calculations at once to the same node. So you don't need a full node to do a benzene molecules, of course. So you can distribute this nicely. But it still needs a bit to run, mostly because of the MPI setup. So the nodes typically need a bit. To set up. So now we have 48, and then we just need one more to get 72, and then we have the 3 batches of calculations done. Check the queue. Yeah. So here user 28, as I mentioned, this is configuring, so you have to wait a bit for the node to start up. Yeah, Vlad, CF is configuring, meaning the node still has to load up, and then once it is, it will run the job. So that's just an AWS specific thing. Okay, so now everything is done. As you can see, my job is also not there anymore. And all of the calculations are finished. As I mentioned, if you do the grep comment again, you will see 72 entries of this have a nice day, meaning everything is done. So I'll wait. Yeah, this will take, unfortunately, 2 minutes or so for the node to start up. But I can just show you quickly the comment. So you do the Python get vibrations, and then you just specify some arguments to the script, which are also described here. Right? So we want intensities of both Raman and IR, which is the M. Right? The P is I want to plot. This is the frequency range, so from 500 to 3400, 1 over angstrom. The folder name, Benz, and then 2 to actually do the analysis, which is the mode of the script. So this will output you also a lot of information, as you can see here. So it's reading in all of the input files here, doing the eigenvalue solving, and so on and so forth. It then points out, or it prints you the IR intensity and Raman intensities for the different modes and so on. Okay. We'll take a look in the second how this looks like. But this is what it will look like when the calculations are finished. And as you can see here, this will give you a lot of different new output files. And you don't need to look at all of them. We will only look at a couple of them. Okay. The way we do it here is we did all the post-processing, so we just copy this again to a local machine, right? And if you remember the rsync comment that we used before. So here, again, important, please use this AVZ option in the rsync. The main reason is that it compresses the files first before transferring. So you have a lot of different now input and output files in that folder, right? You do the initial 72 structures. You have additional input files in there, and this will copy a lot of files at once much quicker. So if I run this, I get again prompted for my password. I put in the password. It copies it. And, oh, that's the wrong folder, but doesn't copy this one back. So if I go in the 1-benzene, this is my output folder where I have the displacements and the relaxations. Of course, I want the displacements. So then you can use something like JMOL to visualize the modes. So as an example here, so this is the full folder of files. bends.xyz contains the modes. So this I will just load. Then you can do the vibration here, and then you will nicely see that JMOL can visualize these modes, right? So it tells you also here which mode it is, right? So this is mode 1. Remember, in the molecule, we have 6 modes, which are just translation and rotation, right? So these ones you don't have to look at directly. And then take a look at all these different modes that you have, right? So you have these kinds of modes, stable frequencies, and so on. I think the one we mentioned here, is the last one, which is the symmetric stretch. So if you go to the last mode, this is exactly this one, right? The symmetric stretch. And as you know from chemistry/physics and so on, here in this case, the dipole moment is not changing, so this should be IR inactive, but there's a change of polarization, so this should be Raman active. And then you can do this for all of the modes in the benzene. But I'm sure you know the benzene molecule at least from experience. So that's just a quick visualization here. And as I mentioned, you also have all of the outputs. So if we do the Benz IR spectrum, you get directly the IR spectrum. And it looks as expected. So you have 2 large peaks around like here 600, as well as 3100 wave numbers. And this already quite nicely agrees here with the experimental measurement, right? Just keep in mind, I mean, we don't have any overtones here, any anharmonic effects, and so on. So it will never match directly the experimental spectrum. You can do the same for the Raman spectrum. And this should look roughly like this, right? Which you can also just compare with literature values. Of course, for the Raman, it's a bit more difficult to find. I think we have not found gas phase benzene for the Raman intensity, so you will probably look at the liquid ones, but they will still match pretty much as expected. And that's how you do IR and Raman or non-resonant Raman spectroscopy for molecules with FHI-aims. In this case, for the benzene. Keep in mind, so we have another part of the tutorial, but this is not part of today. So we have another one on the benzene crystal. The calculations are more expensive for the benzene crystal because once it's a crystal with 40-something atoms, I think, you still do finite displacements and DFPT on top. So this is more expensive. So here we would recommend to just look at the solutions. You can get the folder from the GitLab. So if you take a look here and you scroll down, you can actually just download the solutions. So that contains the input and output files, and then you can just visualize this also after. But that's essentially what's done. So that was the idea for today. Are there any questions from your side, or comments, or otherwise? Also in general, of course, does not have to be related to tutorial directly. David has a question. If you have a polarization calculation but did not add the output dipole, can you get the dipole without running the calculation? I think by default not. So maybe James knows in a bit more detail, but I think you still have to define the output dipole, right? I'm guessing you're referring to, for example, this thing here. Where's the, oops. Here, right? So if you just remove this keyword, would it still work?
So I think I have a feeling the output dipole is like a post-processing step. So with these keywords, you couldn't say rerun it, but you can. There's a keyword called I forgot the keyword to restart the calculation. LZ restart. Yeah, LZ restart. So if you add a keyword LZ restart, SCF converged, then it saves essentially the density matrix of the converged SCF calculation. and then would rerun it for one step to get the dipole. So I just type in.
Yeah, I think the problem is the aims.out, as you know, is just a text file. So we don't actually output all of the quantities by default in aims.out. So I don't think you can just post-process the normal aims.out output. I think it does not contain the information needed for the dipole. So this, but of course, all this stuff here, even the DFBT, is post-processing, right? So if you want to do this, you typically need to use the restart infrastructure we also have in FHI-aims, meaning you don't have to do the SDF in the beginning, and then you just need one step for the dipole after. So I think you cannot post-process directly the aims.out. And then there's a question from Anna. Hi, Anna, nice to see you again. The periodic benzene, yeah, the problem is we have to close the cluster relatively soon, so it will be in maybe 5 minutes or something. So you will not have enough time to actually run the periodic benzene. So, but if you have a cluster available somewhere else and you want to run it, feel free to do so. Otherwise, you can also just inspect the output folder, right? And remember, we also have a session 2. So if you're interested, you can also come to session 2 in the later. Right. But I mean, even then, okay, I have a comment from James again. So the crystal takes like 4 hours to run completely. So you went, not even session 2 will be enough to run it. So keep this in mind. So I would just recommend take the solutions we have in the GitLab and then just do the post-processing. You will not also learn much by just submitting the calculations. So of course you can do all the initial setup and then just copy over the aims files for the geometries, and then that's it.